We're going to be discussing chemical reactions in stoichiometry now. With stoichiometry, that's going to be related to using those coefficients in a balanced equation to help us convert between starting materials, end materials, calculate how much products we're going to get, how much reactants we need to do things. It's going to be a very, very important type of calculation. But it's actually relatively simple in terms of the setup, and a lot of this is going to be just repetition of the same basic concepts. Not always going to be using the same numbers, but the same basic idea is going to be the same. All right, so let's look at what I mean by stoichiometry. If I look at a butane lighter, butane is C4H10, and I use that lighter, I'm actually going to burn that butane, react it with oxygen to form CO2 and water. So I want to get the stoichiometric coefficients out in front of these things. Basically, I want to balance this reaction. So when I balance that reaction, I end up with this. Now, if I have 1.75 grams of butane and I want to know how much CO2 is going to be produced in grams, what am I going to do? Well, I'm trying to convert between two different compounds. The only way I can convert between two different compounds is through a mole-to-mole ratio. In this case, the mole-to-mole ratio is going to come from the balanced equation. Keep that in mind. Whenever you're doing these calculations, the only time, if you're dealing with two different compounds, only time you can convert between them is using a mole-to-mole ratio. Alright, so if I have 1.75 grams of butane, well then I need to get that to moles. I use the molar mass to do that. Then I can convert from moles of butane to moles of CO2. I use the coefficients from the balanced equation to do that. And then I can convert from moles of CO2 to grams of CO2. You can see all my units cancel out to give me just grams of CO2 left. So run that calculation. I end up with 5.27 grams of CO2 produced when I burn 1.75 grams of butane in excess oxygen. All right, now you've seen this before. We've talked about it before. It was that grams to moles, moles to moles, moles to grams type of conversion. All right, so with that grams to moles, moles to moles, moles to grams to moles, we use the molar mass. Moles to moles, we use the mole-to-mole ratio from the chemical formula, or in this case, the balanced equation. And then moles back to grams, we use a molar mass. And keep in mind, these are grams to moles, moles to moles, moles to grams. If I started with pounds, I'd have to get those to grams first. If I wanted pounds, I'd calculate my end in grams and then convert it to pounds. I can add things onto this based upon other mass conversions, prefix conversions, but it all comes down to that mole-to-mole conversion using that mole-to-mole ratio. All right, let's look at another example of this. So I have a thermite reaction, got aluminum plus the iron oxide, goes to form aluminum oxide plus iron. If I want to produce 86 grams of iron, I want to know how many grams of iron oxide am I going to have to use. Well, if I start with the 86 grams of iron, I want to get that to moles. Convert moles of iron to moles of the iron oxide, and then moles of iron oxide to grams of iron oxide using the molar mass of the iron oxide. So that grams to moles, moles to moles, moles to grams, and I end up with 123 grams of iron oxide. Now notice, this was starting with product converting to reactant. I can do any type of conversion I need to with stoichiometry. If I know how much product I want formed, I can figure out how much reactants I need to add in order to get that amount of product. If I know how much reactant I have, I can calculate how much of the other reactant I need in order to get a complete reaction. I can convert between any of these things in this balanced equation. Right? That's an important concept to think about. It's not always going from reactants to products. Okay? Keep that in mind. I can convert between any of these. Now, an added step to this, whenever we're doing these conversions, we need to also be thinking about something called limiting reagents. Now, I can have an excess reagent, a limiting reagent. Excess, that means I have more than enough of it. I have plenty of it. I'm going to have some left over. Limiting reagent, that's going to limit how much product we can actually get. Okay, so going back to the butane example, I said I burned butane in excess oxygen. I had plenty of oxygen. I had a limited amount of butane, so the butane limited how much product it could actually form. Okay, let's look at an analogy of this. If I think about pizza, Say I want to make a pizza, it's going to take 1 pizza crust, 5 ounces of tomato sauce, and 2 cups of cheese to make 1 pizza. How many pizzas can I make if I have 2 crusts and unlimited sauce and cheese? Real quickly in your head, you're going to say 2 pizzas. Now, what did you do to get that? Well, you took your 2 crusts, and you knew that 1 crust would make 1 pizza, so you did a conversion. You ended up with 2 pizzas. Now, in this example, what would be the limiting reagent? Well, the limiting reagent would be the crust, right? We have unlimited sauce and cheese, so the number of pizzas we can make is going to be limited by how many crusts we have. That's just for this example. So let's look at another example using this analogy. So I'm starting out with the same combination to get 1 pizza. Well, let's say this time I have 3 crusts, 20 ounces of tomato sauce, and 4 cups of cheese. How many pizzas can I make from that? Well, that's where we're going to have to look at each individual reactant to see how much product could be produced. So if I have 3 crusts, convert that to pizzas, I get 3 pizzas. If I take my 20 ounces of tomato sauce, convert that to pizza, I could get 4 pizzas with that much sauce. Take my cheese, convert it to pizza, I get 2 pizzas. So out of all of these, what's going to be the limiting reagent? The limiting reagent is going to be the cheese. After I make 2 pizzas, I'm out of cheese. I have no more left. So the most I can make is 2 pizzas. That's it. Now, since I only make 2 pizzas, that means I have crusts and tomato sauce left over. Well, how much crust and how much tomato sauce do I have left over? Well, 2 pizzas would require me to use 2 crusts, so I'd have 1 extra crust left over. 2 pizzas would require me to use 10 ounces of tomato sauce, so I'd have 10 ounces of tomato sauce left over. So I can even calculate how much excess reactants I have left over. Okay, so that's the analogy there. Be thinking about that analogy. Let's look at some actual chemical reactions with regards to limiting reagents. So if I have 5 moles of O2 react with 6 moles of H2O, here's my balanced equation. I want to know which one's limiting, which one's excess. Well, to do this, take my 5 moles of O2, figure out how much product would be produced. So I'd get 10 moles of water if all the oxygen reacted. Take my hydrogen, set up my ratio, I'd get 6 moles of water produced. So which one is the limiting reagent? Well, the most water I can get is 6 moles of water. Therefore, the hydrogen is the limiting reagent because I've run out of hydrogen after making 6 moles of water. I'd still have moles of O2 left over, so the O2 is going to be excess. All right, let's look at another example of this. If you look at the thermite reaction again, if I have 5 moles of aluminum react with 3 moles of iron oxide, how many grams of aluminum oxide are produced? Well, in order to figure out the maximum amount of aluminum oxide I can get, I have to figure out which is the limiting reagent. Now, because it's asking about mass of the aluminum oxide, I'm just going to take my reactants and convert it to mass of my product. And since it's asking about the aluminum oxide itself, I'm going to convert it to mass of aluminum oxide. If it's asking about the iron, I'd convert it to mass of the iron. Okay, so start with my 5 moles of aluminum, do my mole to mole conversion, do my mole to mass conversion, and end up with 255 grams of aluminum oxide. I have to do the same thing with my other reactant. Unless I'm told that the other reactant's in excess, I have to do this with both of them to determine which one's the limiting reagent. So 3 moles of iron oxide, do my mole to mole conversion, mole to mass conversion, I get 305.9 grams of aluminum oxide. So which one of those was the limiting reagent? The limiting reagent was the 5 moles of aluminum. Once 255 grams of aluminum oxide has been produced, I've used up all my aluminum. I have no aluminum left over. I'll have excess iron oxide left over. Maximum amount I could get is 255 grams of aluminum oxide. Now notice, limiting reagent isn't dealing with the moles of the reactants. Okay, you have to use that conversions. Because if you just look at the 5 moles of aluminum and 3 moles of iron oxide and say, oh, well, I've only got 3 moles of iron oxide, therefore it's limiting because I have a smaller amount, that's not true. We just went through an example where the iron oxide is actually in excess. Okay, so don't just look at those initial numbers and go, oh, I'm just going to go with the smaller one. You have to do these calculations to determine what the limiting reagent is. Once I've determined how much of a mass of a product I have, I can then deal with something called theoretical yield and percent yield. All right, theoretical yield is the amount of mass I should produce. That's what we just calculated. In theory, I should get this amount of mass. Now, when I actually go into the lab and run an experiment, there's so many other factors that come into play other than just limiting an excess reagent that can affect the outcome of the amount of product I get. Okay, so with percent yield then, what I do is I take what I actually get in a lab experiment, divide it by theoretically what I should have gotten based upon my calculations, multiply it by 100%. All right, so let's look at that problem we just worked. Right, we ended up saying that the aluminum was the limiting reagent, and we should have produced 255 grams of aluminum oxide. Now let's say I run that experiment in the lab and I only end up with 204.9 grams of aluminum oxide. For whatever reason, I didn't have it hot enough. There's other factors that came into play. I didn't let it run long enough. For whatever reason, I ended up with 204.9 grams of aluminum oxide. So my actual yield is what I get in the lab. It's at 204.9. Theoretically, I should have gotten 255 grams. Divide those by each other, multiply by 100%, and I get my percent yield. So it's 80.4% yield. All right, so let's run through some examples. And what I'm going to do here is I'm going to show the example problem and then slowly go through the steps, but I'm not really going to talk through the problem at all. Okay, so here's the first example problem. So why did I use the 5.31 grams of N2? Well, that's because my limiting reagent was CuO. Let's look at another example. So I'd end up getting 5 grams of manganese oxide produced in this, and my KMnO4 would be my limiting reagent. One thing I want to note out of this, when you look at this problem, it looks daunting because there's a lot of stuff in here. But it's actually the same calculation. You just have to know what information do you need to pull out of there. And don't let really complicated equations or reactions throw you off. We're still dealing with mole-to-mole ratios. And that's it. So the only thing I pulled out of that chemical equation was that 14 moles of KMnO4 was producing 7 moles of Mn2O3, and 4 moles of the C3H4OH3 is producing 7 moles of the MnO2. And that 4 moles of C3H4OH3 is producing 7 moles of the Mn2O3. Right, so don't be daunted by these. You still have to stop and think and pull information out, but don't look at it and immediately go, oh, this is impossible, I'm just going to skip it. Alright, so let's look at another example here. Alright, in this example, instead of starting with a mass, we're starting with volume and a molarity. Because we're starting with that volume and molarity, we can still get to moles. Alright, it's still the same basic idea, it's just a different method of getting to moles now. So I start with my volume in liters, multiply by my molarity, and then I can do my mole to mole conversion from the balanced equation. And then I can multiply by the molar mass if I'm looking for mass. So for that particular one, I'd end up with 1.34 grams of strontium sulfate. And you need to do that for both reactants, though. Okay, and I end up with 3.65 grams of strontium sulfate for that one. So which one's limiting, which one's excess? Well, limiting is the Na2SO4. The excess is the SRF2. The amount of solid precipitate I can produce from this is going to be the 1.34 grams of strontium sulfate. So all of these are focused around that basic idea of that mole-to-mole conversion. What I start with to get those moles may be different. What I do with those moles at the end may be different. I may end up with moles at the end. I've converted them to grams. I may end up with those moles and have to convert to a molarity. Okay, I can do that. Each problem is going to be unique, but it's going to focus around that mole to mole conversion. Just think about what units am I starting with, try to get those to moles. Once I've got my moles, then I need to get them to whatever units I'm wanting. I'm going to show some problems, different types of problems, and leave it up to you to work those if you want. One big thing I want to point out in this one is that this shows nothing but names and amounts, and it's asking for molarity at the end. You need to be able to solve a problem by knowing the names as well. So keep in mind, when you're working these problems, all these things we've been talking about up to this point, they've been building upon each other as we've gone along, right? We started with simple mole-to-mole conversions, then we went from grams to mole conversions, then we had volume and molarity to moles. Now all of those things we keep adding on more and more. You need to get these things down and know how to do those individual steps so you can do those steps together. Practice these problems. There's lots of problems out there that you can practice on. It's going to get a lot easier if you just keep practicing these types of problems dealing with this stoichiometry. That's all I'm going to talk about with stoichiometry for now, but we're going to see stoichiometry again and again and again.